Alright, welcome back to particle physics and standard model. This is lecture 50 and in the last class we wrapped up our discussion on fixed target versus head on collision configurations and we looked at some examples of this intensity frontier versus energy frontier. Using a real life example we worked out the virtues of using the head on collision configuration to produce new particles, right. And then we moved on to a very important concept in particle physics and all of physics, if you ask me, which is that of cross section. So the cross section is determined by the number density of the target and the length of the detector, if you will, right. That is what we saw. Ultimately it all comes down to finding out what the mean free path is, right. So the mean free path should go as 1 over number density of the target that you are studying and the compensatory quantity that you introduce to get the dimensions right is nothing but the cross section, and in this case it is the scattering cross section, right. And the important thing to remember is that the scattering cross section is not something that is determined by you, it is determined by nature, okay. It's a quantity that is intrinsic to the system that you are studying, the beam and the target that you are studying. What you can do is to arrange the number density and the size of the system, size of the detector and so on, and count the number of hits to measure this intrinsic cross section, okay. So you can either think of this as one projectile hitting a number of target particles, or maybe a beam of projectiles hitting one particular target, right. So that is the notion we moved on to, which is what is usually done in real life situations. One example we saw of that was the Rutherford's gold foil experiment, where indeed he threw an alpha beam on a fixed target of gold foil particles, right. Where now you measure the number of beam particles that scatter, and in particular if you measure how many beam particles go into what direction, you get these differential rates with respect to angle, which gives you differential cross sections, and similarly you can have differential rates with respect to energy or any observable that you want to construct. And this contains even more information about the interaction between the particles, yes. And finally we wrote down a general formula for the differential cross section with respect to anything, right. I just have to take the differential number of scatters that I get, then I divide by the flux of the beam that I am thinking of course, times the time it takes for the entire scattering to happen, right. And I had promised that I will now generalize this to just 2 by 2 scattering, right. So how will I do that? I can still think of some sort of a flux, okay. We will see what that means. Let us first see how to modify the numerator here, okay. So in particular the case that we are dealing with is what happens if I expect to have the number of scatters smaller than 1 in that particular situation, okay. This can happen for instance if t is not large enough, right. If I do not wait too long, if I only shoot the bullet once, okay, on a rock, I am asking what is still the cross section. In other words, we are asking for the probability, not the number, right. The probability of scattering to happen divided by the flux times the time, okay. The probability of incident particle to scatter, okay. Said differently, we are in this is a technical term, optically thin regime, okay, where I am thinking of the total number of scatters expected is less than 1. Okay, so what is the total number of scatters? So let's go back here. Let's look at this equation for instance, right? So the number of hits is cross section times the number density of the target times the length of the detector, right? That's what I've written here. So that's the total number of scatters I expect as the bullet passes through the bunch of balloons. And if I expect that number of scatters to be less than 1, it means the cross section is so small, right, that we are in the optically thin regime. In other words, the detector is almost transparent to the bullet. Okay, that's where the optically thin comes from. Okay, so let me also write, just means we are in the transparent regime. Okay, in that case I can only talk about the probability that it will hit the bullet, right? This can be contrasted to the other regime. No prizes for guessing what that is called. Optically thick regime, where when the bullet goes in, I am sure that it will hit at least one balloon. Okay, so if the cross section is large enough, definitely it's going to hit at least one balloon, right? So in other words, the detector is opaque to the beam, correct? Good. So that's how what I'm trying to say here is that basically the equation that we've written down here for 2 to 2 scattering corresponds to the optically thin regime naturally, okay, when we start talking about probabilities. So we are going to indeed use this to get a general expression for the cross section. But before we get there, I want to make use of this notion to talk a bit more about certain useful quantities that are being used in real colliders. Okay, this will just take me 5 minutes. So we have the differential cross section. So maybe I'll write this bit in a different color to show that this is a little bit of digression, but it's a useful digression. Okay, so the number of scattering events, okay, that I can expect given this cross section, okay, can be written as this, where this L int, okay, is the integrated luminosity. You might have heard of this phrase in the context of colliders. Let's see, if you open any popular science news article on the Large Hadron Collider or other colliders, you will hear this, you will see this phrase. Okay. Now what is integrated luminosity? For that, let's look a bit more into what we mean by luminosity. We say integrated because we have literally integrated over some other quantity, which is the luminosity. So what could this luminosity be? Just look at the previous expressions that I was writing down. Look at this and this, or look at over here, look at this and what I've written down here. See that luminosity is nothing but the flux of the beam. Okay, again the luminosity has units of 1 over centimeter squared per second, right? So one other way to write it is using barns, but okay, let's just write inverse centimeter squared inverse second. Okay, since you now integrated over this, what should this be? The units, this is just inverse centimeter squared. Of course, you can also see this from the equation on the left itself. On the left hand side, I just have the total number of scattering events, which is a unitless quantity. Since I have a cross section on the right hand side, the integrated luminosity should have inverse centimeter squared, right? But in practice, people use a different unit, okay, for both cross sections and luminosities, and that is to say that the cross section is some prefix with a barn. Have you heard of this barn units? What is a barn? It is 10 power minus 24 centimeter squared. Okay, it was introduced in nuclear physics historically, but now everybody uses it. Okay, this is a more convenient unit. Instead of every time we saying 10 power minus 32 centimeter square and all that, we can just express in terms of barn, and you immediately know what people are talking about. Okay, that would mean the integrated luminosity has units of inverse some prefix barn. So what is this prefix? It could be femto, milli, and so on, right? So for example, the integrated luminosity could be expressed in terms of some inverse femtobarn. Okay, and that would mean the luminosity could be expressed in units of some inverse femtobarn inverse second. All right. In fact, as of September 2024, okay, at the LHC, the total amount of luminosity, integrated luminosity accumulated is around 349 inverse femtobarn. Okay, the more the time passes, the more integrated luminosity that you accumulate. It's just the flux of the beam. The flux also keeps increasing actually. Okay, they keep increasing the flux, but then as time also increases, put together the total integrated luminosity increases. Now this is a measure of how much data you actually have, right? Because the cross section is set by nature, right? So you increase the luminosity, integrated luminosity, you're going to get more events. The more the events you have, the more scatterings that you do see, the better it is for your analysis. The statistical precision gets better, the more things that you can look for, it's just overall better. Okay, so for that reason, these quantities are very central to collider physics. Okay, and to give you some idea, in the future, in the not so far future, people are thinking of putting in another collider called the high luminosity LHC. Okay, it's called sometimes HLLHC. Why is it that? They're not going to change the energy of the beam. The aim is to get 3000 inverse femtobarn of integrated luminosity. That just means what? 10 times more events than you have today, right? That gives a lot more statistical precision to the searches that you want to do at the LHC. Okay, and this may go operational in 2028 if everything goes well. Okay, so that's a digression. I hope it's a useful digression so that you can see all of these things have very real life applications right now. We can get back to deriving the general expression for 2 to 2 scattering. Okay. So we started with this, right? I'm just going to now rewrite that as, okay, let's hold on. Yeah, I'm going to rewrite that as, I'm going to keep the differential probability, okay, and I'm going to keep the time downstairs, okay, but I'm going to write the flux in a certain way, okay, because it's just 2 to 2 scattering. It is nothing but the magnitude of the relative velocity. 2 to 2 means what, by the way? It means, you know, I have 2 particles coming in, some scattering has happened, and I get 2 particles coming out, right? So we are talking about the velocity of this and the velocity of this. So the flux now is nothing but the relative velocity, and then what else? What should I divide that by? By some volume within which this scattering is happening. Agreed? So let me write that explicitly so that it looks clear. It has the right units, that much you can give it, right? But it is what it, this is exactly what it is. Okay, for 2 to 2, this is how you would think of the so-called flux. All right, so V is the volume within which the scattering is happening. So this is our starting point. Okay, now we need to figure out what each of these quantities actually is, and in particular what this dP is. So of course it is the probability for the incident particle to scatter, but in terms of you know, what you do have here, like, you know, the 4 momentum of the initial state, 4 momenta of the final state, and so on, what could that probability be is what we are trying to find here. Okay, and I'm going to claim that that probability is, I'll write down the quantity and then we'll see what it is. Okay. That times this quantity. So what does this stand for? This is basically, okay, a something of a transition amplitude to go from an initial state to a final state, where this S, what is this S? It's just called the S matrix. Remember this again from quantum mechanics. The S matrix contains a term that accounts for no transition. This is just, you know, plane waves going into plane waves, right? If an electron is just traveling along, that's captured by the first term, which is nothing but the identity. Okay, but crucially there is a transition amplitude also, right? And this is called the transfer matrix. I think people also call it the transition matrix, but basically it captures the transition amplitude. Correct? So I is the initial state, you have to go to some final state, and there is a transition amplitude that is captured by the S matrix, right? In fact, we can define the S matrix in this certain way. This is in the Heisenberg picture. Okay. we can re-express this in the Schrodinger picture, where my final state is something that I take at infinity, and the initial state is at t equals minus infinity. Okay, so here the states evolve. In the Heisenberg picture, it is the matrix that evolves. Correct? So, in other words, I am taking asymptotic states. Okay, I am taking an initial state at t equals minus infinity, and then I am asking what has happened to that state when I go to t equals to infinity, and that is captured by this S matrix. All right. So, basically the S matrix contains information on the time evolution of the initial and final states. Okay. So, these are basically asymptotic states. So, if you have forgotten all this, go back to your quantum mechanics or advanced quantum mechanics or whatever and refresh your memory on these concepts. Okay. So, given that I have to take the correct norm, so that is what I have done in the denominator, right. I have taken the self norm of the final state and the self norm of the initial state also, and then I multiplied it with this weird d pi. What is that? That is another crucial ingredient in all this. Okay. The d pi is colloquially called the phase space. Okay. That is nothing but, see, the final state can span some range of momenta, right. So, this is nothing but the region of final state momenta that is of interest to this particular process, this particular probability. Okay. Okay, if that is a mouthful, let us just write an expression, it will become clear. Okay, so in other words, this is d pi is nothing but, now this pi is different, this is a product of basically the total number of available states in phase space. So, how do you write that? It is just this, right. The volume times the volume of the Brillouin zone that you are thinking of, that is the momentum volume, divided by 2 pi cubed, right. So, these are all the cells, number of cells in phase space, both real space and momentum space put together, correct. So, for 2 to 2 scattering, we can explicitly write what that is. For each particle there is a V, so I have a V squared, and then for each particle in the final state I have a dqp3 and a dqp4, and for each I have a 2 pi cubed in the denominator, so I am just going to square it. Okay. So, this is for 2 to 2 scattering. If it was 2 to 3, I will write one more term, V cubed, then I will put a d cube p5 and then one more 2 pi cubed in the denominator. Okay. Okay. Now, there is one more thing we need to work out here. Okay. The denominator of this dp, this norm, right. So, In quantum mechanics, right? Oops. If this had been just quantum mechanics, this would have been 1 and this would have been 1, right? But we are not in quantum mechanics, we are in quantum field theory, correct? So here it's not 1. Okay, so let me just write first. It's not 1, we have to actually calculate what that is. And it's not that hard. I'll give you the answer first. I'll give you one answer first and then we'll see how it works. Okay. If I have a state defined by, if I have a one particle state defined by its momentum p. Okay, let me write this. One particle state then this is nothing but 2 pi cubed 2 omega p, where omega is the energy of that state, times delta cube of 0. Okay, so where did this come from? This follows from a few different things. Okay, this might look a bit tedious, but it's all important. Okay, see, if I act this operator, the creation operator, on the vacuum, what do I get? I get a particle state with momentum k. Yes, but this has a certain normalization. Okay, so I'm going to make use of that, and then I'm also going to make use of the fact that if I have the annihilation operator acting on the vacuum, I get a null vector. Okay, and then finally I'm also going to make use of the commutation relation which we had written down long ago when we looked at Klein-Gordon, the Klein-Gordon equation, Klein-Gordon action and all that, right? So in the solution we had these operators, remember? And this was the commutator that we got, right? So put all this together and make use of the fact that, like before, this delta cube 0 is nothing but the volume. Remember how that came about? So I'll just quickly remind you. That came about from the fact that we know this is true. If I take some momentum, that's nothing but the Fourier transform of 1, right? So that means if I take p to 0, right, I get volume over 2 pi cubed. Yes, so it's actually volume over 2 pi cubed to be exact. So this is what we are going to make use of. Okay. Okay, so that's clear. Basically, we are putting in, we are going to make use of these commutators. That's how we get. So basically, this k is what I just promote. I just I take the square root of 2 omega to the other side, and I have the I have an expression for the p state, right? And then I do the sandwiching. I'm going to get basically the square of that square root of 2 omega. That's what I'm getting here. Okay. So putting all this together, I have this norm is nothing but, instead of omega p, let me just write EP. Okay, so 2 EP, now 2 pi cube times delta cube of 0 is nothing but the volume. Okay. Now that means if I take the initial state, right, what is the initial state here? I have two particles in the initial state, right? Initial state is P1, P2 together. And the final state is P3, P4. So this norm is nothing but 2 E1V to E2V. Yeah. And similarly, the final state is nothing but, the final state norm is 2 E3V to E4V. That's it actually. Okay. So this is now actually good enough for this class. We are now going to plug in all these things back into the expression for the probability, and from there we'll derive the cross section, and we'll also see the notion of transition amplitude and the matrix element. Okay, the most important part, the matrix element and Lorentz invariant phase space. So all of this we will deal with in the next class. All right, thank you.